Hello, friends! Good news, everyone!
Uh-oh, I don't like the sound of that.
I am still alive, and better yet, I got my master's degree. Call me Casual Gamer Master of Science. With all that extra time on my hand, I will focus on providing you guys with more quality content. Starting right now.
But you know what I like a lot more than materialistic things? Knowledge.
That's a hacking group we've been reporting on that's claimed responsibility for recent attacks.
Today won't be a tutorial, instead I will give you an overview of my thesis. When I asked you guys many months ago, the majority of you guys voted, you will watch anything, so let's give that a try. Alright, first things first, what was even the goal of the thesis? So, as you can read here, estimate the reliability limit for future IMF studies in the Galactic Center using the ELT. Now initially, when somebody stated this objective to me, I had no idea what this even means, and I probably am right to assume that the same is true for you guys. So let's pick this sentence apart a bit. First of all, what is the ELT even? ELT is short for Extremely Large Telescope. This is not a joke, the astronomers are pretty creative with their namings, I guess. So yeah, the ELT currently under construction, it's a telescope which will be capable of taking very high resolution snapshots. For us, most interesting near the galactic center, so near the black hole at the center of our Milky Way galaxy. Then what is the IMF? So we are interested in IMF studies. The IMF is short for Initial Mass Function. Here you can see the initial mass function or the sample resulting from one such initial mass function, which is basically just the density and then the amount of stars within or for a given mass, right? So given a certain mass, you can see how many stars will have that specific mass when sampled from a set of stars. And that set of stars in our case will be a star cluster, but it can be anything, it can even be a whole galaxy, right? So what is the mass distribution of a whole galaxy? That would also be described by an IMF. And so we want to study this IMF. What does it mean? So we want to determine the shape of the IMF of star clusters near the galactic center. And well, it's pretty easy for high mass ranges of stars because they are easily detectable. But what about low mass stars, right? Can we detect them? Are there too many other stars? How reliable can we say if the star belongs to a cluster or if it's just a field star? Meaning some star we do observe with our telescope, but it does not belong to the star cluster itself. It's just some other star in the front or in the back. And so this makes it pretty hard to detect the true stars which do belong to the cluster. Some of you probably already think, and rightfully so, that we will be using clustering algorithms to determine the cluster membership. Okay, so in other words, the goal of this thesis, again, it is to determine the reliability of cluster membership detection. Meaning, if we observe some stars, how reliably can we say if all the observed stars for each individual one, if they do belong to the cluster or if they don't? Because if we know that, that's the same as knowing the initial mass function. We just assume that once we know the stars, we can quite accurately say what mass they have. Okay, so starting with the project itself, this was just the goal. First of all, what will we do, right? We will simulate stars, we will observe those simulated stars, and then we will perform this analysis on those stars. Meaning we will determine if they belong to the cluster, if they don't belong to the cluster, and then judge how reliable those results are. Right, so here you can see I used a database, or I created a database rather, consisting of some tables. One table for the simulation itself with all the parameters of the simulation, one for stars, so those are field stars, cluster stars, both the simulated stars and then later on the observed stars. Each having, of course, velocity and position for different time steps. So at a certain time, what is the velocity, what is the position of each individual star. And then down here, we have a separate table for some analysis. Most interesting here probably is the total energy. So if I simulate stars, if they evolve over time, right, the positions do change, of course, but the total energy of the system must be conserved. So recording this is kind of a decent test to see if the simulation does what it's supposed to do. Okay, so when simulating stars, of course, first of all, we gotta initialize the stars, meaning we gotta set initial mass, initial position, and initial velocity. And for that, I used an open source package named McCluster. And, setting some initial parameters, not going into all the details here, but it does result in up to over 40,000 stars. So that's quite a high number, which does make it quite challenging to compute all the velocities and the positions in the future, because all the positions of each star depend on all the positions of all the other stars, or rather the force acting on one star, right, results from all the other stars. So with a naive algorithm, this would scale with n squared. It's called direct summation. This would scale with n squared. And of course, this is not an option when we have n over 40,000. We can't do that. So what I ended up implementing is the Barons-Hutz algorithm, with does scale with n log n, which is of course way better than n squared. So the algorithm is way faster when it comes to computing the force between all the cluster stars. And here we can see a comparison. So this is my implementation. Here in blue, you see the data resulting from my simulations for a different amount of cluster stars, and then the time required. So of course it still goes up, right? With the amount of stars, the time needed for the velocity, for the force calculation does of course increase, but it only increases with n log n, not with n squared, right? Here in green, you can see n squared, and the n squared would be way worse. Okay, so when simulating cluster stars, or when time integrating cluster stars, the force between the stars does not only depend on the other cluster stars, but of course it depends on the whole Milky Way, right? It's inside the Milky Way somewhere, and of course all the stars of the whole Milky Way to some extent influence the velocity of the cluster stars. So what I ended up doing is model the whole Milky Way with a potential as well as a density. So the density describes the distribution of the stars of the Milky Way, and the potential can be used to calculate the force on the cluster stars. But the density can be used to initialize the field stars. So field stars, again, any kind of stars which does not belong to the cluster. But you have to imagine, if we look into a certain direction, right, we will see all kinds of stars, not only our cluster stars, but also all kinds of other stars. And we will use the density here to initialize those other stars. The components of this potential here in my model is a black hole at the center of the Milky Way, disk stars, bulge stars, so those are different kinds of Milky Way stars, and a dark matter halo. Now, when initializing the field stars, I can't initialize all the stars of the whole Milky Way. This would require way too much hardware, I guess. That's not an option for my home computer. So I only initialize the stars within the volume that I can observe with the telescope. And this is defined right here. You have the position of the observer, you have the view direction, right, the direction you're looking at, and you have some angle, right, the angle of view, the view angle, which is how far you can see to the left and to the right. And resulting this cone over here, I call it the cone of vision. We are only initializing the field stars inside this cone of vision. After we have initialized those field stars, right? Well, actually, how do we even initialize those field stars inside this cone of vision, right? So first of all, we determine with integration the total mass from the densities described earlier. We calculate the total mass of all the field stars inside this cone. And then we sample mass functions. You remember this initial mass function earlier. We sample individual star masses from these functions until we end up at this total mass. And in fact, for those field stars, we get up to over 350,000 field stars. Now, remember from earlier, 40,000 stars was already quite the issue. now imagine 350,000, right? That's even way more, almost 10 times more. So of course, quite challenging for the home computer. One has to be careful to be quite efficient with the code. But nevertheless, so this is the amount of field stars we end up with. And then of course, we do not only need the mass of those field stars, we also need the positions and the velocities. The positions I get from sampling the densities, and the velocities from solving Jean's equations. And here we can see one such results from initializing field stars. Here we are looking straight through the galactic center, right? So this is a pretty extreme situation. The observer is only 2 parsec from the galactic center. This is of course very close, right? I mean, the Earth is at a distance of like 8,000 parsec. So of course, this observer is very close to the galactic center. It's looking through the galactic center, and we are sampling all those field star positions. And well, these are quite a lot of stars, of course. And I use this setup just to see, well, if the algorithm performs well in this kind of scenario, then of course, in a less extreme situation, it will perform as well. When initializing the velocities of the field stars, we have to use a lot of approximations. So here what I did is I compared data resulting from my simulations with observed data. So those points with those lines, this is observed data, and those lines, those squiggly lines going through here, this is from my simulation. So I would say works quite well, right? So I'm plotting here the velocity dispersion of bulge stars, more specifically from my simulation versus observations. And when it comes to simulating the real world, it's always, of course, very important to compare the results from the simulations with results or observations from the real world to see if the simulation is good enough. So this is basically why I did this test over here. Works quite well, could be even better, but decent enough for my purposes. So after initialization is complete, we have all the stars, we have all the masses, we have all the velocities. Now we need to integrate the equations of motions pretty much to get the snapshots of those stars at different time steps, right? So we have at time step 0, or at the current time, we have the positions, we have the velocities. Now, well, what will be the positions and velocities in, let's say, 7 days, right? So this is why we integrate the equations of motions to get those future positions and velocities. Then we write this data into our database, which I showed you earlier. And then we do a test on the total energy to see if the total energy for all those different snapshots is roughly the same. If it is, then, well, integration worked decently. Now the simulation is complete, right? And actually, at this point, maybe it's I should show you a short movie, right? Inception over here, movie inside movie. Here you can see this is a cluster simulated using my software. This is a cluster, and here you can see it's X versus Y. So this is in the galactic plane, so to speak, how the cluster moves over time. Those are all those small dots here are individual stars. And how does it evolve over time? So yeah, this is only the cluster itself. So here we do not simulate the field stars, but for the cluster itself, looks very good in my opinion. And well, this is the results over millions, if not billions of years, the evolution of all those stars. For us, we don't need that. We don't need billions of years. We only need days, right? So days between observations will be required for our purposes. But nevertheless, I did this huge simulation just to see if the algorithm works long term. Okay, so continuing on, after having all those stars and having those different snapshots, so having the stars at different time steps with all their velocities and positions, it's time to actually take images, right? So remember, the goal is to see if the ELT will be capable or will be usable to study the initial mass function. So of course we need to simulate images, or we need to generate images in a way how they will be generated using the ELT. For that, I will use a Python package. This is something I didn't write myself. So up to this point, I wrote pretty much everything myself. But this Python package is available. I used it. But it does require some preparations to use this package. And first of all, so far, the coordinates, so the positions and velocities, are given in galactocentric Cartesian coordinates. Meaning galactocentric, meaning the galactic center is at the center of the Milky Way. And Cartesian, well, it is a Cartesian coordinate system, right? Now we transform all the positions and velocities over to heliocentric telescope polar, I called it, which means heliocentric, meaning the sun or the Earth or whatever, the observer pretty much is at the origin. And then polar coordinates, well, I hope you know what polar coordinates are. And so far, we have star masses and the distance to the observer. And what we need instead are so-called spectra of the stars. And we can convert pretty much from using mass and distance, we get the spectra. And we also take extinction into account. What is extinction? It's pretty much, let's say, dust between the source, so between the star and the observer, takes light away, so to speak. It reflects, in a sense, some part of the light coming from the source. So it is dimmer than if there was no dust in between, right? So we do have to take this into account, which we do here. And then using this package, ScopeSim, we get the images. So here you can see one example of one such image. And here you can see some issues, right? Here you see these spikes over here, those called diffraction spikes. And well, remember what our next goal is. We have those images, and from those images, we want to figure out which stars belong to the cluster, which are field stars. So we have to get the stars out of these images. And well, those lines over here, right, they are a problem, because they could be detected as field stars or as any stars, right? But they are no stars. They are artifacts. These result from taking the images. So this is pretty much a limitation, so to speak, of the telescope, right? The telescope is to blame for these things. Those are no stars. So when extracting the data, how do we deal with these issues? And I will show you how I did it, but it could most certainly be improved. So let's talk about getting those stars, the position of the stars, and also the flux, which is kind of like how bright they are, right, out of those images. So for that, I used yet another Python package. Was somewhat forced to use that. It's called FOTUtils, and more specifically, I used the method DAO Starfinder. There are some parameters or some relevant things regarding this method, but most importantly for us here, or what I want to talk more about, is the masking. So what is masking? What masking allows you to do is essentially say, well, in this region, right, I do not want to detect any stars. And this is what I used in order to deal with those diffraction spikes, right? So these issues coming from those images, I do not want to detect those spikes as stars, right? They are no stars. So what I ended up doing is masking the regions around bright stars and only accepting the brightest source, so the one in the center, as a real star, and all the others are ignored. If they are diffraction spikes, then good for me. If they are real stars within these regions, well, then I just don't detect them. So let's look at the result from this extraction process. Here you see again this super bright star, and well, maybe you can see here in green, this is the bright star itself, it got detected, but nothing around it got detected. And of course you can also see here many real stars, which did not get detected at all, right? So this is a limitation of my extraction, but at least the ones that do get extracted, that do get detected, I can say with quite high certainty that they indeed are real stars. So now we have extracted the stars from the images. What's next? Well, performing the clustering algorithm, of course. But some preparations again. So first of all, I mapped the observed stars, meaning for all the observed stars, I found, the simulated stars which resulted in these observed stars, right? So what's the simulated stars corresponding to the observed stars? And another thing that I did do is approximate the velocity. So remember, we took images, we extracted positions from these images. So how do I get the velocity? Well, I take 2 images in close succession, so to speak. So between the images, maybe there are 7 days in between, or maybe 20 or 30 days between those images. So I have 2 sets, or I have 2 images. I overlay them, so to speak. I find which star in the first image is which star in the second image, and from that I can get or I can approximate the velocity of that star. And why? Why the hell do I want the velocity? Because remember, we want to figure out which stars are cluster stars, which stars are field stars, and from the positions alone, this is pretty much impossible. But, excuse me, but from the velocities, it is very much possible. So looking here at the velocities, here you can see velocity in one direction, velocity in the second direction, resulting from this velocity approximation. And here in blue are the velocities of the field stars, but here zoomed in all the way from the cluster. Here in green, these are the velocities of the cluster stars. So you can see they are very close to each other compared to the field stars. So this is a very nice basis or a very nice data to perform a clustering algorithm on. So what I ended up doing is only using the velocities and completely ignoring the positions themselves. Well, the velocities are calculated from the positions, so in that sense I do take them into account, but not directly. So right, so how to do the determination of which clusters or which stars are cluster stars? For that I use the dbScan algorithm. It's density based, right? Remember, here we have high density of velocities. So density based is definitely a good approach. And with noise. So noise in our case is any star which is not a cluster star should be determined as noise. So any field star. Quite a nice algorithm. I can go into more detail about this algorithm in another video if you're interested. What's also nice about this algorithm is, imagine we take images and maybe there's not one cluster inside this image, maybe there are 3 clusters, who knows? This algorithm doesn't care if there are 3 stars, and if it works properly or if it's set up properly, well, then it detects all the 3 clusters. If there are no clusters, it detects no cluster. So that's also a benefit of this algorithm, I guess. So, okay, so we use the clustering algorithm, we have some results, right? The result of the clustering algorithm is, oh, this star is a field star, this star is a cluster star, but can we trust these results, right? So for this, I use the F1 score, which takes into account false positives. So false positives are field stars wrongfully classified as cluster stars, and false negatives, it also takes into account. False negatives are, of course, cluster stars which are observed, but which are classified as field stars. So also, again, a wrong classification. And how can I even know this? How can I know which ones are false positive, which ones are false negative? Well, that's because, remember, let's go back here, I map the observed stars. Meaning, for the observed dataset, I have the simulated dataset, and of course, in the simulated data, well, these are the initializations. So here, of course, I know which one is in fact a cluster star and which one is a field star. So this is the reason why I can even judge the performance of the clustering algorithm. And yeah, well, this is the F1 score. It's a result between 0 and 1. The closer to 1, the better. As you can easily see here, right? True positive, meaning true positive is a real cluster star classified as a cluster star. So that's perfect, of course. And then if we only have true positive divided by true positive and all those false, right, all those errors are 0, then of course we get the amount divided by the same number, and that's 1. So that would be a perfect score, would be 1. Anything below that is not perfect, but well, the lower the worse, pretty much. So let's look at results. Here you can see for stars between 0.08 solar mass, meaning solar mass is the mass of our sun, right? So 0.5 solar mass would be half the mass of our sun, all the way down to 0.08. So for stars within this range, the clustering algorithm, when looking at the galactic center, here at degree 0, it performs the best for clusters which have a total, a very high total mass. Down here, you have different total cluster masses in kilo solar mass. So this is 25,000 solar mass clusters, which is quite high indeed. Here you can see we get better results, right? This is a lighter red. It's closer to 1 than, well, here on the left for a very small cluster. And at the angle 0, so looking at the galactic center, right, it's worse compared to when looking at the galactic anticenter, so looking in the opposite direction of the galactic center. Of course, over there are way less field stars, so the clustering algorithm tends to perform better. Some nice images, but let's also have a look at some numbers. So here again, for stars with less than 0.5 solar mass, with the highest or the biggest cluster overall, we find only 28% of stars, but the F1 score is 0.76. Again, remember, the higher to 1 the better. So you can see here, well, it increases, right? It's a direct correlation between the cluster, the mass of the total cluster, or the cluster mass, and the score, 0.76. This is quite good. So meaning this is kind of my prediction, right? I will say with the ELT, we will be able to perform clustering with at least such a score. I would say in reality, it will be possible to get even way better results than this one. So I would say mine is a quite low estimate. This is because, well, I only use the velocity for the clustering algorithm. One could use different things, like let's say one could estimate the distance between the star and the observer potentially, and then use this data as well to perform the clustering algorithm. So I only use the 2D velocity, and still the result is pretty decent. So this is quite promising. I'm looking forward to the real results, which we will hopefully get in a few years, and let's see how good my predictions hold up. With that, thank you very much for your kind attention, you guys. Wow. Yeah, this has been a very long journey, 2 years in the making pretty much. And well, if you're interested in more of this scientific stuff, if you want to see more details, of course, this was very rough overview. If you're interested in more details, let me know in the comments below. Right. But my old me will take over now. I recorded the rest before, so see ya, guys. If there's any part of this project you guys would like to know more about, let me know in the comments below. But that's it for today. As always, thank you very much for watching. Until next time, friends, talk to you soon. But that's it for today. Thank you very much for watching. Scheißdreck.